dear students. Today we have proposition 16 of book 3. A straight line drawn at right angles to the diameter of a circle falls outside the circle. And further, a straight line cannot be interposed in between the circumference and that straight line falling outside the circle. And further, the angle of the semicircle and the remaining angle will be less, or are less, than any acute rectilineal angle. I'm going to explain all that, okay? So here's our circle, and here's our diameter. Oh, and by the way, a corollary to this prop is going to be that straight line which falls outside the circle touches the circle, doesn't cut it, so it touches. We call that a tangent in modern language. Okay, so here we have a circle, here we have the diameter. Thus it is required to show that the straight line drawn at right angles to that diameter falls outside the circle. It doesn't come in any way whatsoever within the circle, okay? And then it's required to show that once that's shown, that right angle is drawn, that there cannot be a straight line interposed between the circumference and that straight line falling outside the circle. There cannot be a line interposed in there, put in between here and here, okay? And notice, when you talk about here and here, that's an angle, but it's no longer a rectilineal angle. This would be a rectilineal angle. This would not be a rectilineal angle because one of the lines is curved, okay? So, and we're going to say that the angle of the circumference, that is to say, the angle formed by that diameter and the circumference, that's called the angle of the circumference. You can check the definitions. And the remaining angle, that is to say, here you have the angle of the circumference, and then the angle between the line touching the circle and the circumference, that little bitty angle, that the angle of the circumference is greater than, and the angle remaining is less than any acute rectilineal angle. Rectilineal right angle, let's do it this way, rectilineal obtuse angle, maybe, obtuse angle, and then rectilineal acute angle. An acute angle, as we know, is any angle less than a right angle. An acute rectilineal angle, any acute angle less than a right angle. Okay, so that this will be greater, the angle of the circumference is greater. Notice it's not a rectilineal angle, made up of a straight line and a curved line, the circumference. That the angle of the circumference is greater than any acute rectilineal angle, not than any angle, any acute rectilineal. And the remaining angle is less than any acute rectilineal angle. The smallest acute rectilineal angle possible, this remainder will be less than it, okay? What we're going to use from our bag of knowledge today is that any two angles added together in any triangle are less than two right angles. And remember that the exterior angle plus its adjacent angle together were shown equal to two right angles. And this was also shown equal to the opposite interior angles. Therefore, this and this are equal to two right angles. I don't remember. Anyway, we showed that the two angles added together are always going to be less than two right angles. Yeah, that makes sense, because this is equal to these two, and this are equal to two right angles. So that is obviously less than two right angles. And if it's equal to this, these two are also less than two right angles. Okay? So let's get cracking here. Let's draw our angle. We'll draw our thing at right angles. I say that it falls outside of the circle. For if it doesn't fall outside, there's two possibilities. If it doesn't fall outside, it either falls within or it falls on the circumference. A rectilineal angle falling on the circumference is ridiculous, but we're going to grant that for Mr. Smarty Pants' sake, okay? So let's do some things here. Let's say, okay, well, let it fall within, Mr. Smarty Pants. Here's our angle. Let that be a right angle, say. Here, and that's required. You have to draw an angle, right angle. We're trying to prove that it falls outside, and the possibilities falls within or falls on. Let's show a reductio here. Let's take the center. Okay? Now we have a triangle with one of the angles being a right angle. The other two added together are going to equal a right angle as well. The interior angles of a triangle equal to two right angles. We proved that. Therefore, one of them is less than a right angle. So here you have a triangle, this angle being right, this being less than a right angle. And we showed that in any triangle, the greater side subtends the greater angle. So this will be greater than this, but it's equal. Okay, because these are radii of the same circle. Okay, so this is greater than this because this subtends this right angle and this subtends the supposed less than a right angle, less than a right angle. So this is not equal to this for that reason, and this is equal to this because they're radii of the same circle. So here you have radii of the same circle, so there be an isosceles triangle, this equal this, and therefore the angles at the base of an isosceles triangle are equal. So those are equal in one way, when looking at it from the truth of the matter, but looking at it from Mr. Smarty Pants' position, this is less than this because this subtends the acute angle and this subtends the right angle. Okay, so this is both equal and unequal. This is both equal and unequal to this at the same time in the same respect. That's absurd. Okay? So we're not going to hold that. Now, the same thing would happen if it fell on the circumference. You would have this and this being equal in one respect because it would be an isosceles triangle. And because this is a right angle, this would be greater than this. So this would be both equal and unequal to this at the same time in the same respect. That's a problem. Well, if it doesn't fall within and it doesn't fall on it, it obviously falls outside it. Those are the only three possibilities. Therefore, we have shown that if there be a circle and a diameter be taken and a straight line be drawn from the diameter at right angles, that straight line so drawn and extended will, because it's right angles on this side too, will fall outside the circle. And then the corollary is, therefore, it touches the circle. Now let's show the second part of the prop, that it can, another straight line cannot be interposed. Okay? We're going to do that. What are we going to do second here? That it can't be interposed. Yeah, let's do a straight line cannot be interposed. Okay? For if it were interposed, okay? Say it's interposed like this. Okay? Now let's, to that line that's interposed, let's drop a right angle from the center. We know we can do that, given any straight line and a point not on it, to drop a right angle. And it's clearly, because it's interposed, it's not going to fall within. Okay, nor is it going to fall on. So this is dropped at right angles. Okay, now here you have this triangle. Here you have this triangle with one of the sides being a right angle. Therefore, the one of the angles being a right angle. Therefore, the other angles are less than a right angle. That's no problem. It would be less than a right angle. Therefore, this is greater than this. Okay? This subtending a right angle. This subtending something less than a right angle. This will be greater than this. But look at this here and this here. They're radii of the same circle. Therefore, this is equal to this. So therefore, since this is greater than this, and this is equal to this, this is also greater than this. The part being greater than the whole. We know that the part is less than the whole. So here we have this thing being greater than this line being greater than this line, and not greater than this line at the same time in the same respect. Okay? So we just shown that it would be impossible to interpose another straight line between the circumference and the straight line touching the circle. Great. Now, what do we want to show here? We want to show that this angle here between the circumference and the diameter, making up there, is greater than any acute rectilineal angle. and that this angle here is less than any acute rectilineal angle. Okay? Now watch this. Look at this angle. I say it's greater than any acute rectilineal angle. This is a right angle. Any acute rectilineal angle would have to fall within. So it would have to be interposed right here. So it would be, say, something like this. But we just showed that you can't interpose another straight line between this straight line and the circumference. So for there to be an acute rectilineal angle greater than this angle, that other straight line to make the acute rectilineal angle, rectilineal, both being straight, would have to be interposed. It's obviously not going to be over here because it would be greater than a right angle. For it to be less than a right angle, it has to fall short of this angle. If it falls short, the only way for that to happen is if it were interposed. For it to fall short and be greater than this, it has to be interposed. And we just showed that you can't interpose a straight line between the circumference and that. Likewise over here for this little angle, there cannot be any other acute rectilineal angle which is less than this angle. This is a very tiny angle. You can't make an acute rectilineal angle less than this angle here. Why? Because you have to interpose that line. And we just showed that you can't interpose a line. Okay? Therefore, we have shown that if there be a circle and the diameter be taken, that the straight line drawn from the terminus, from the end of the diameter, at right angles, that straight line so drawn will fall outside the circle. And then the corollary that we end up showing is that it touches the circle. Further, that there cannot be a straight line interposed between that circumference and the straight line which falls outside the circle. And further, the angle of the circumference is greater than, and the remaining angle less than, any acute rectilineal angle. Quod erat demonstrandum. Thank you. Bye-bye.